because I think it's one of the things that is probably not very well understood by a lot of people on the Foxborough, the people that are doing the Foxborough engineering, no matter who that is. And it's another one of those things that's not very well explained or documented. And it's the BPC statements, okay? In a base processing cycle on a control processor, it's going to run at a fixed frequency, 1 second, half second, tenth of a second, 5. So you can set the BPC for your control processor. And it's going to execute the blocks in a compound inside of that, assuming it can do it with no overruns and do its thing. And one of the parameters for a piece of sequence code, let's go to, is the base processing cycle statements, okay? And here, I think the default is 100, but in this case I've set it to be 10 statements. So it's going to run 10 statements. If you put it in an infinite loop before it throws out, it's going to execute 10 statements, and then it'll say, okay, I have to break and give the rest of my processing time back to the processor. And you can set that number to go up to, I'm not sure what the max is. I think it's 1,000, but I haven't got the book in front of me. But it gives you an idea of what you can do with that. So I've got these set for 10, 100, and 1,000. Okay. So, and the code itself, let's go look at one that we've got open right now. These are all going to look the same. Okay. In this case, we've got a loop that's just going to loop forever. And we're going to go in here, and in this case, we're going to read our seconds off integer input 1, which is going to get the seconds from the station block. And then we're going to show that value on integer out 01. That's actually a loop count, and then we're going to show the number of seconds on integer out 02 just to prove that we read it and are showing it. Okay, so this is about as tight a loop as you can write. It's all internal values, no external references, and we're just going to demonstrate the different. If I toggle this, these three will go active. It's the exact same code doing the exact same thing, but with a different BPC statement count. Okay, and so this is the number of the seconds off the clock, and this is how many statements it's executed. This seconds is a station second timer, so it's just going to roll back around, and these will keep counting up. But you can see when I toggle this active bit off, that 10, 100, 1,000, that is exactly what we would expect for the number of the difference between these as they go up, right? It goes up by 10 each time, and that's what it's doing. Now, the more you put one up here with a higher statement count, the more stress you're putting on the processor itself. If we go look at the station block, what you'll see is, and in this case, the sequence block will go up because when we run all of these, because it's putting a lot more load on that, and you don't give it a chance to break out of it. So if we go back, and I've got a lot of other stuff behind the scenes tied to this, but if we do that, what you have happen is, see, our sequence block amount, which this controller has nothing but this in it, starts going up. And you can overload a CP by putting enough type block, station block, well, not station block, but enough type code with a BPC statement number that's very high in several blocks, you start running into performance issues. But there are other things to take into account as you do that. So we'll go to the next piece of this and look at it. So I'll stop running these, and I'll get the next one.
Hey, David, I got a question on this. So say you had come across a sequence that had like a while true do statement, and then within that, just an if statement. So basically, you just had it continually looping, and each time it looped, it would check, you know, the if statement and execute whatever code's inside of there. Would having a lower BPC in that situation help to relieve some controller loading issues?
Yes. Yes. If you have a lower BPC in that, you will reduce the loading issues. But what we're going to discuss next, though, is I'm going to show you what happens when we start doing like some unsecured reads, and you get into some interesting things with this. This is the same code over here, but instead of reading in the number of seconds and writing it out, which here we're bringing it on integer N01 and writing it out, here we're actually just doing an unsecured read. So if we were to go look at this, I can show you what that looks like. Let's go look at it. And we'll take, this is a local one. So we say edit sequence logic, edit source, and notepad. So you want to reload it, and it does. And now you're going to see here we're looking at the station second. So this is an unsecured connection. And you start with a colon, and then we have the station block. We're reading the number of seconds. Everything else in the code is exactly identical as the other one. Same tight loop, same everything. Okay, so if we hit this button, they're going to both start. And as you can see, the numbers are identical between the two. Okay, so even though one of those has got a secure connection coming in on integer N01, and the second one is making an unsecured call, but it's in the same CP, and that's going to be important for the next part of this, because now we've got, so if you see, this is a tight loop. We don't have any reads, we're just all internal. Here we're doing a local, one unsecured read. These are identical, okay? But if we go pick up another guy, okay, and now we're going to do remote unsecured reads. And again, all of these are tied to the same thing, but now we're going to go read the seconds from a different station block, okay? So watch what happens when we start this. Notice that even though the Bpc STM, here I have 10, 100, 1000, the actual number of loops that it's executing are identical. It doesn't matter, because anytime it sees a read, an unsecured read, where it has to do a peer-to-peer connection, it's stopping that, making the read, and coming back on the next cycle on that processor. So this loop, to do the exact same thing, ran 15,333 times versus 45. Okay, so this is very important. If you're reading a peer-to-peer connection, even if you have a BPC of 100, this is the performance hit that you're taking to make that unsecured read to go from peer to peer. You're getting a tremendous amount less process. So if you were to bring that in, make a secured connection to one of your inputs, and then do it, you would be good. So does anyone have any questions about that?
Yeah, I was just wondering if you could explain the unsecured versus secured terminology. That's not something that I guess we have used at our company.
Okay. Well, okay, I can do that for sure. Like an unsecured connection, or to go read one of these, like in this particular instance, here we have when you are writing sequence code, we can either bring in a variable, let's go to, let me get out of this one and go back to this guy. If you look at integer input 1 on this, you're going to find that here we have a secured connection. We brought it in on the integer in 1, and we've got a compound block parameter that we've got coming in. Okay. If we go to the local reads, it may still be there, but we're not using it. But no, it's not. So I didn't have a connection to integer in 1. In this case, if we look at the code, the source of this block. Okay, so now it'll load when I do this. Do I want to reload it? Yes. Okay. When you do this, it's the same thing is now coming in as we've got the compound block parameter just written in the code. And if you start that with a colon, the sequence code will go out. It'll make that object manager connection to that, and it will read this. Now, also, if you're in the same compound, and this is not, so I can't get away with it, but if you had some variable, if it's in the same compound, you can lead it with 2 colons to make a local variable, and that even saves some lookup time. I'm led to believe the first time through it says, hey, I'm in the same compound I'm in. You can have the block and parameter and bring that into a variable here. This one is going to go out to the object manager table, but it's going to find it in the same control processor that I'm already in. It's going to put it in there, and it's going to read it very quickly. Okay, but now if we make that same connection to a different CP, which is what we're doing on the other one, which is this, when we make that connection across to another CP, it says, okay, I've got to stop my processing, make that peer-to-peer connection, get that value, bring it in, load it in, and so every time it's doing that on a unsecured read, it's making that wait. So what we could do, for instance, let's do this as an example real quick, because yeah, we got like plenty of time. So let me close that. And we'll do, this is a remote 100, and we'll just make a copy of it. So we're going to say remote, but with a secured connection 100. So we've copied our block type. We've got the same. We should have all the same. That is not the button I wanted to push. This will stop in a second. Hang on a second. So we'll go ahead, and what we'll do is we'll copy this logic there.
While you're getting that typed in, I just thought I'd add something a little off topic that we've run into with unsecured connections and sequences. There is a limit to the amount that you can have inside of one independent sequence block. It's pretty large, but you can hit a limit for that. You can add subroutines that include, or that basically extends your limit if you want, but just thought I'd throw that out there.
Yeah, the book says, and I don't find this very well documented, but it says the external reference table will support 40 external references. So, but that, I don't see that in any, real tables or anything. I just have one instance of where it's got that. So I'm not sure what the right answer on that is. So, okay, we made a copy there, so let's, real quick, we'll go in here, and what we'll do, instead of going...
I've got a question.
Sure.
On the updates, so if you had those 40 updates.
Yes.
And they were being processed at different locations inside the code.
Mm-hmm.
Would it go out and read them as they're encountered, or is it smart enough to know that I need to update these 40 pieces of these memory locations at once?
Okay, my understanding is that every time it hits an unsecured connection to a peer-to-peer, it will stop the execution of the sequence code to resolve that. Now, I could write something to check that. It'll take longer than I've got to do right now, but we could do that and verify that that's how it works. So here we just want to say,
I know it catches the limit on when you compile the sequence. So I guess I was thinking that maybe it built a table of all the unsecured connections when you compiled it, but I don't know that for sure.
well, the ones on the, the ones that are local, I know that it does, right? It keeps them all and it just runs right through them because it's still doing those object managers. It just knows they're in there. But the peer-to-peer object manager ones, it would be good to get a better understanding. And I can, like I said, we can do a little bit of research and come back and have an actual answer on that. I know for a fact that when it hits one, it's going to, like we're seeing it do now, it's going to stop and go out. Now, whether if you had 3 unsecured in a row, does it stop on each one, which I think it does, or does it go, okay, I've got a table with these, I'm going to stop, update all of my peer-to-peer connections, and then continue, the next cycle. I'm not sure about that. Okay, so we've got a read seconds in, and it's coming in on integer N01, I hope. It is, and so we can come back and do the same thing. Okay, and let's see, so we edit all of our block parameters. So that we're reading the same thing that is FCP 501. So we got that guy in there now. Okay, and it should be the equivalent of this. So if we were to come in here and take this guy. Call it remote secured 100. Let's see what happens if we do this. Sequence logic, make sure we compiled it. Good there. Okay, that one hasn't been run, but these have all got something to initialize them, so they should start out the same. So the question will be whether or not this and this, the difference in the way that these operate. Well, apparently they don't operate at all. Let's take a look at that. Okay. Good point. You do have to checkpoint if it's on a different CP to get that to work across. So let's see what those look like. Okay, so our checkpoint, we've got a number coming in on our seconds. And that's secured, so can't do that. let's make sure that we've got the remote seconds 100. And I said something different in this, didn't I? On my block that I did here. Well, that looks okay. Let's take another look. Better. Okay, so now we're doing the exact same thing, but without doing that peer-to-peer connection, same number of block processing steps. And now you can see that it's matching what we have up here in these without having to do that peer-to-peer unsecured connection across them. So if I stop this, these three all match. This is doing the exact same thing that this is doing, but it's doing it with a secured connection coming in on that integer input. So this would be a good explanation of why you want to avoid peer-to-peer connections in your sequence code with any unsecured connection, because the processing power, it's tremendous difference in executing 1,400 statements versus 42. And that gives you some idea of why you would want to do that. Now the other thing is, on the same thing, back to the base processing cycle statements, anytime that the control processor, anytime the code comes to a wait statement, it's going to stop execution for one processing cycle. So if we have something where it says wait until, or you put wait 1 second, or wait anything, it's going to take that and it's going to stop the execution at that point and then pick back up when it comes back. So I think the thing to know is the base processing cycle to be important. Yeah, Ishmael said that he expected the compiler to optimize secured or not, but what it does is, if it's unsecured, I don't think it can do that. It doesn't know what to do as far as getting that table set up, because you can construct, right, an unsecured block on the fly in the sequence code. So there's no way for it to know what that's going to look like ahead of time. But when you're working with variables where it's already named, then it can go out there and it can put that in a table, and then it's just looking it up in the object manager table, I assume. But otherwise it says, I've got to stop and go figure out what this really is, and then I can take the value and come back. So this is a key point. This is the point I was trying to drive home on this, is the fact that that's something that requires a amount of thinking about how you construct your code. Same thing about hitting a wait statement. If you can avoid that, and you're trying to do something that needs to execute in a hurry, so you're taking a moving average or something like that, anytime you can avoid those type things, you get better performance out of your sequence code. I have one other item to show that I don't have really on the screen here, but the other thing is, and I was expecting a little bit different result on that, but we have one where we're doing some writes as well. And in this case, we're just writing to a dummy analog in block. And the whole point of that is just to give me something that I can write to, okay, as we go through here. And if we go look at this write, BPC writes, what we find here, if I stop it and restart it in this, I don't know if I've got this one tied in or not. So I was expecting here our block statement is 1,000, and so you would expect 1,000 per cycle or something close. And I think we see that it does go pretty close to that versus you can see it's jumping up by several hundred a time, 500, a little, yeah, around 500 each time that it's doing that, and that would make sense. But this is doing an unsecured write, but it's in the same CP. So not as, I thought that would actually cause a performance hit where it was doing that even in the same CP, and apparently it doesn't. So that's something to be aware of as well, that it treats it just like when we were going back up here and doing these local unsecured reads. A local unsecured write does not have a very high performance cost associated with it. So that's my discussion of the Bpc STM parameter. If people have anything else they'd like to add, I'm certainly open to that.
Hey Dave, just one maybe closer to a real world example of this that at least I've seen before is like, you know, when are you going to be doing a bunch of these unsecured connections? Well, one example is if you're like checking a train of valves or something. Something somebody might try to do is save their Boolean inputs. If they've got to check 10 valves for whatever reason, open and close limit switches, that's 20 values they're trying to read. So the first thing you might try is like, well, I'll just make these unsecured connections instead of using block parameters. And that's when you really would see a major performance hit if you're trying to read 20 values in a, you know, 20 unsecured values makes a, you know, potentially 10-second delay, depending whether you always read them or not. So in that case, just what comes to mind is maybe using an external calc block to check all 20 of those values instead of trying to read them all within sequence code.
Exactly. If you don't have enough parameters to make secured connections to all of those peer-to-peer connections, going through an additional block and condensing them, like you just said, go through a calc block or something, process them, and then hand them into your sequence code gives you a much more efficient sequence code than going out for an unsecured peer-to-peer connection. Now, and the other thing is, if you are running low on connections, if you have some that are local, some are in the local CP and some are in a remote CP, you would like to take all of your unsecured connections that you're working on and make them in the local CP, so you don't have the performance hit of going outside that CP on those connections. So that would be another best practice.
Does the BPC parameter only apply to sequence blocks, or is it also a parameter in calc blocks as well?
It's only in sequence blocks. I am not sure if a calc block, I mean, I know when a processor overruns its, you know, control cycle and has too much in it, it'll stop and then pick back up the next one. But I don't know that it'll ever stop in the middle of a calc block. I think that it would always execute, you know, to the, I guess, the end. I know you can put a calc block into like loops or statements. I'm not sure how it determines where it needs to exit a calc block.
Dave, I don't think there's any way to do a loop in a calc block, right? If you try to jump up, it won't let you.
Right. So I would say, and I see that others are weighing in, I think a calc block runs to completion. I would agree with that. I can't think of an instance where I could get one that's not, you know, but it knows the state it was in last time, right? So if it's got a one-shot pulse for a number of seconds, the next time it runs through, it's still maintaining the fact that it was in there. It keeps a history, I guess, and that's why they have that clear history parameter in a calc block to determine whether or not it knows where it was when it initializes and things like that. So I know that they can do that, but I do believe, like, you know, that it runs all the way through.
Gotcha. Something along those lines with, I guess, best practice, maybe more for calc blocks, and maybe that's a different thing we can do at some other point. But I know we've come across in the past a lot of calc blocks that don't have an end statement in them, and from my understanding is it runs through all 50 lines in the calc block if you don't add an end statement after your code. So generally, for best practice, we've gone with adding an end statement after our last line of code.
And yeah, I've seen that both ways. I don't know that I don't know. We can do some, that would be something. If we start getting into calc blocks, which is another whole area, the amount of testing and checking and doing on those would be very high because, one, they're very tight. They don't have a lot of steps. And I don't know that if it does some amount of processing on an empty step or if it just, basically figures out that it doesn't need to go there and jumps to the end anyway. But yeah, to be able to do that would take we'd have to write a whole lot of them to do a test where we could see some performance hits in the controller. So
I had a question, Dave.
Sure.
You showed very well the impact on secured and unsecured reads on that specific block. How about the impact, the differences of secured versus unsecured on the station loading?
Oh, I can answer that. Yeah, if the station loading will go down because when it hits an unsecured read on a peer-to-peer, it basically is like hitting a wait step, and so it frees that. It stops the execution of the sequence block at that statement, and you'll see your performance. The performance of these right here on the CP loading is much less than the performance of these that are wound tight and are running really hard. Even though this has a BPC of 1,000 and these have a BPC of 1,000, these are doing a lot more to your processor on the CP than this is, even though this is having to do more with the object manager and go out and do those peer-to-peer connections. And you would see that in I don't have it set where I can turn individual ones off and on the way I've got it set up right now. But in the station block itself, you can definitely see a difference as you wind them up. When you put a higher blocks per number of statements per base cycle, it really makes a difference on how loaded this is. See, and we have one peer-to-peer point, which is accurate. So, this is showing you kind of what we've got there. So I think that's, go ahead.
Now, how about the object manager scan? Does that show any difference?
Wait, back up just a second. There is a network loading recommendation that you minimize the number of unconnected or of unsecured transactions to 10 per second. I'm not sure if that's seen at a single station or across the network, but 10 per second is beyond that you load up the network, they say. Now, that guideline also came out with node bus stations. I don't know how it impacts the higher speed mesh stations.
And I don't either, but, and I would comment on that. We try to avoid as much as possible peer-to-peer connections all the time. I mean, it's a good practice to try not to have them anyway. But there are situations that we run into where you wind up needing a peer-to-peer connection to do something. And I understand that too. And I agree, you want to minimize them all the time. I don't know I also don't know what the amount is that you can do on a mesh network now, because in theory, right, they've got actual routing going on in the switches so that the CP to CP, once they establish that, it's not doing an object manager broadcast once it's got an object manager table set up and knows which CP it's in. So it shouldn't be flooding the network. Those routers ought to be, you would think, minimizing the traffic. I don't know if it really does that or not. So that's what we know about that. But I think I think it's something that people don't have a very good understanding of, the BPC STM parameter. I think that it doesn't behave the same way, like here, if you have those external connections versus here. These all started at the same time. So it's something to bear in mind. It's something to think about when you're writing sequence code that requires an answer, something where you're doing a lot of heavy calculations before you proceed. It's good to know that. And I think that this is I hope, something that you guys got some value out of as a discussion point about writing better sequence code, because I think that it's something that bears looking at. And if I'm writing something that is, if I've got a tight loop, I will take a look at it and say, do I care if this loop executes multiple times in a BPC? And if the answer is no, I'm calculating one thing, or I'm doing something, I'll either put a wait statement in that loop so that I don't have it. I say, well, I can execute all these statements in one BPC, and there's no reason to have it run through this loop 6 times or however many times it can do it in a BPC. So you can be smart about how you write your code in a way that maximizes your CP efficiency. And the way you can be smart is you can say, okay, I'm going to avoid, unsecured peer-to-peer connections. I'm going to avoid unsecured connections if I can. I'm going to certainly make an effort to avoid an unsecured peer-to-peer connection. And then even more than that, if I've got a loop and I do want it looping forever for whatever reason, then that's not uncommon to set some up and say, I'm going to repeat until some event occurs or whatever. At the bottom of that loop, when you're just sitting there in a while loop or something like that, you can put a wait statement so that it won't sit there and process that loop multiple times on that CP. And that's a smart thing to do. You just have to look at your code, and it's kind of code dependent on how you do that. Any other questions or comments? Well, if not, I hope everybody enjoyed this and maybe got a little something out of it. And hopefully we can, do this again in another month, and we'll pick another piece of topic on sequence code, and we'll try to, consolidate some of these notes and everything and get this to so that people can take a look at it, and maybe we'll get a little better as a group of writing and editing sequence code. So thank you, everybody. I hope you enjoyed it.
Thanks again for putting this on, Dave. Appreciate it.
Thanks.
Thank you.
Mm-hmm.
Oh, I was also told to ask, is this going to be recorded to be put up at some point?
Yes, we recorded this one, unlike the first one, so I had to go back and do a whole nother thing. So maybe we'll edit it down and try to make it a little tighter. But yes, it's been recorded.
Okay, thank you.
You're welcome.